So let's just go through this example. So with the mean value theorem here, we've got to show. Well, let's remind ourselves what the conditions are that we need in order for the mean value theorem to work. So f needs to be continuous on the closed interval a, b, and differentiable on the open interval a, b. Then the conclusion is there is at least one point C in the interval AB where f prime of C is equal to f of B minus f of A over B minus A. So let's kind of put that into context here. So we've got, in this case, the interval from -2 to 2. So our A to B would be that. So let's actually fill it in here. Putting -2 to 2. So there has to be at least one point C in the open interval from -2 to 2, where f of 2 minus f of -2 is equal to 2 minus -2, or is over 2 minus -2. So let's see, what would that be in this case? So we can kind of work out those values here. What's f of 2 and what's f of -2? Well, actually, here before I do this, let's first verify those first conditions here. So this is a polynomial. So is it continuous? Well, yeah, we know polynomials are continuous for all x. And is it differentiable? Yeah, we know polynomials are differentiable for all x. So those two conditions are all we need for the mean value theorem to apply. Okay, so we see those two conditions are satisfied. So we know the theorem here will guarantee that there is at least one point C in the interval from -2 to 2, where the derivative at that point is equal to this average rate of change. Okay, so that's our goal, is to now solve for this point C that satisfies this condition. So let's work it out here. F of 2 would be 2 times 8 minus 3 times 2 plus 1 minus f of -2. So that's 2 times -8 minus 3 times -2 plus 1 over 4. Whatever, let's see, what do we get here? 16 minus 6 is 10 plus 1 is 11. And then here we get -16 minus plus 6. So -10 plus 1 is -9. We get 20 over 4, which is 5. So we want to now solve when f prime of x is equal to 5. Okay. So in this case, actually finding f prime isn't too bad. That's just taking the derivative of 2x cubed minus 3x plus 1. So that'll be 6x squared minus 3. Solving it out here. So let's see, I'll add the 3. We get 6x squared equals 8. Dividing the 6, we get x squared is 8 over 6 or 4 over 3. So x is plus or minus the square root of 4 over 3. Or 2 over radical 3. Notice that those points are both on the interval from -2 to 2. So these are both equal -2 over radical 3 and +2 over radical 3 are in that interval. And these are 2 points where we know the slope is equal to 5. Okay, and here's a picture, right, where we see there's the curve, and we see on the interval from -2 to 2, there are these 2 points where the slope is 5. Yeah, Zoom's weird. Are you guys all getting kicked out, or is it just some of you guys?
No, I got kicked out for like 5.
Okay, well, hopefully it's recording everything, and we can just, you guys can watch it later to see if you missed anything. Yeah, sorry, I don't know what's going on with Zoom. Something's obviously up with Zoom because it's very unusual. So hopefully it's recording everything, and then you guys can see what you missed later. I hope. But let's try and just finish it up, and then we can move on. So just a couple of quick consequences of the mean value theorem here. If f is differentiable and f prime of x is equal to 0 at all points on an open interval I, then f is a constant function on I. So what this shows is that if I have a function whose derivative is always equal to 0, we know that it must be a constant function. So actually, we know kind of one direction of this would be that if I do have a constant function, then the derivative must equal to 0. So this is actually going the other direction, which says if we have a function whose derivative is always equal to 0, then it must be a constant function. And so, well, let's kind of think about how the mean value theorem might apply here. So assuming f is differentiable on some interval AB, then we know there exists some point C with f prime of C equal to f of B minus f of A over B minus A. Since we know by the assumption here that the derivative is always equal to 0, we know that, yeah, f of B minus f of A over B minus A will equal to 0. So if I multiply B minus A over here, we have f of B minus f of A must equal to 0, which means that f of B must equal to f of A. And this is for any value of A and B. Notice that a and b here was chosen arbitrarily because here we're assuming that its derivative is equal to 0 at all points on some open interval. So if I just take any a and b that are in that open interval, then hopefully, or sorry, if I take any a and b that's on that open interval, then we've got here that they must have equal function values. So the conclusion is that here, oops, Jesus, okay. F of a must equal to f of b for any a, b in the interval I. So that means it's a constant function. And one more consequence of this is that functions with equal derivatives differ by a constant. If two functions have the property that f prime of x equals g prime of x for all x on an open interval I, then f of x minus g of x equals a constant. So that means that f and g are basically the same function with just maybe a different constant. So we can easily apply the previous theorem here that if I let h of x equal to f of x minus g of x, then h prime of x is f prime of x minus g prime of x, which must equal to 0, since f prime of x equals g prime of x. Yeah, it's okay if you guys are being kicked out. I'm just going to keep going, and if you guys are getting kicked out, we'll just keep going, and hopefully it's recording it so you guys can watch it later. Anyways, so since f prime of x is equal to g prime of x, what we're assuming here, then we know the difference must equal to 0 for all x. So by the previous theorem, that means that h of x is a constant function. So that means that f of x minus g of x must be equal to a constant for all x.